Okay, first we have a brief review of the trigonometric functions. In the future, we will use the short notation. Just use trig for short. And you will see this very often. Trig functions is short for trigonometric functions. Four of them. And in the future, we'll learn a few more, but these four are the most frequently used ones. And we have this complementary angles. Okay. Jessica, can you hear me, Jessica? Okay. So what are the definitions of complementary angles? Maybe Kira. Complementary, another one is supplementary. Okay, Amy.
Complementary would equal 90,
Mm-hmm.
and then supplementary equals 180.
Okay. If we draw a figure over there, if this is alpha, this will be beta. They are complementary. And if we draw another pair, if this is alpha, this is beta, they are supplementary. So complementary and supplementary. Then the formulas of trig functions for complementary and supplementary angles. So here we can solve beta from it. We can solve beta from it. Okay. All right, now let's check how are these functions related to the cosine sine of theta itself. Okay. Aaron, first one, cosine supplementary.
Let's see now. That will still be cosine.
Okay, think about it. So supplementary, complementary, what's the difference?
Well, for cosine, the hold on, sorry. Supplementary would be negative cosine.
Okay, so you know this one is correct.
Mhm.
Cosine theta. But for supplementary, you can see cosine alpha corresponds to sine beta. Complementary angles, they change, they switch sine and cosine. Okay. And Kira, what about this one?
Negative sign?
Okay, so for the supplementary angles, cosine have negative sign, but sine
No, the
has the same,
sign's still positive, I think.
still positive, yes. Okay, so with these two formulas, we take a quotient, we can get a formula for tangent and cotangent of complementary angles. Amy, tangent.
Cotangent theta.
Cotangent theta. And Jessica, cotangent. Peter, what about you, Peter? Okay, maybe not yet. Let's give the answer. Tangent theta. Okay, so we can see for complementary angles, sine and cosine, we switch. Tangent and cotangent, we also switch. But for cosine and sine of supplementary
I have a
angles,
question.
yes,
Isn't cotangent for the complementary one supposed to be negative tangent? I'm just curious. Is it?
you mean here?
Yeah.
So let's check. How do we define cotangent?
Cotangent equals 1 over tangent. Oh, wait, never mind.
Okay. So now this one, tangent will be sine over cosine, have a negative sign over there. So this gives us this is difference and similarity between these two groups of formulas. One for complementary angles, one for supplementary angles. For complementary angles, switch, but for supplementary, one stay the same or still positive, but the other three are negative. Okay.
Wait, is that negative thing because of the x-axis?
Yes. So very soon, when we study circles, we will extend all four functions to more general angles. Okay. And a very useful formula, I think you all know this one, is the area of a triangle. If we can draw a perpendicular line, then the area, 1/2 base height. In our case, base is BC, AD. But we can use angles to represent the height. We have a right triangle over there. So sine will be the quotient of the opposite side over the hypotenuse side. Multiply both sides by AB. And we plug this into the area formula. And so the difference between these two formulas essentially the same, but this one we do not need the height. We just need length, and sine of this angle. Area formulas. So from there, we derived the law of sine. A, B, C. So sine angle, the opposite side, sine angle, the opposite side, law of sines. Then another very important one, law of cosine. Okay, we check with cosine B, just for example, so cosine B. There are different ways. First, the product C. Importance of this formula is let's consider a special case. If this is 0, then what we have here is a Pythagorean theorem. It should be a right angle. So this is the generalization of the Pythagorean theorem. How far is this triangle from a right triangle? It's this part. Okay. So from there we can solve cosine. Law of cosine. Okay, so these are the formulas we have learned about the trigonometric functions. Next one, we'll learn another formula, find the area. It's called Heron. Some say Heron, some say Heron, just different spelling of this. So again, we have a triangle with 3 sides. For this new formula, we introduce a quantity called the half perimeter. This defines the half of the perimeter. Then the area. We don't need anything about the angles. We just need the size. Okay, let's first see a few examples. Example 1. Let's consider the following triangle. A equals 3, B equals 4, C is 5. For this one, let's find the half parameter S. Then find the product.
Excuse me?
Yes.
I have a question.
Uh-huh.
Is that A or a C?
Uh, is A or C? You mean here?
No.
Or line above or line below?
The
Oh, I see. On the triangle. You are right. So this mistake should be,
sorry.
you are right. Should be A. Yes. Okay, I will give you a few minutes, maybe a few seconds to find what is the half perimeter S.
It's
Uh-huh.
a half perimeter is a 6.
6. How did you get this?
So I added 3 plus 4 plus 5, that's 12, and
Mm-hmm.
half of 12 is 6.
Okay. Okay, so the next one will be the product. First, S itself. S is 6. S minus A, 6 minus 3, which is 3. 6 minus 4, which is 2. 6 minus 5 is 1. So this will be 36. Okay, what's the area? Amy.
The square root of 6 times 3
Uh-huh.
times uh 2 times 1.
Mm-hmm. Okay.
That's 6, right?
Mm-hmm. Okay.
Yeah, check. I
Okay.
got something.
So according to the formula, the area should be 6. How do we check this? Is this correct or not? So this is a very special triangle. Who had seen this number before? 3, 4, 5. Okay, Kira, what are the specialties of this triangle?
Like if it's a right triangle, then five would be the hypotenuse and the B are the legs. So like 3 squared plus 4 squared equals 5 squared.
Okay, very nice. So this one we have A squared, B squared, is C squared. If we draw a right triangle,
Wait, then that means that also works. This example also works on right triangles.
yes, but it's more general. We start with a special case.
But okay, I see.
Okay, we'll have more examples.
That means 5, 6, and 7 are also special.
No, no. That's
They
a
give that
general.
example on the paper.
Yes, yes. Yes, they're not special.
Oh, okay, so
Okay.
that's why this one's special. I see.
So for this one, for right triangle, how do you find the area?
For right triangles, it's basically half base times height, right?
Okay, which is
Or either half length times height, but that works.
also 6. So you can see the two results match.
The areas, right?
Uh-huh. Okay,
Wait,
next one. Yes, Aaron.
can I write this down?
Okay. 5, 6, 7. Now we can check a squared plus b squared is different from c squared, so we cannot do that. But we can still find the half perimeter, the product and the area. Let's go that way. Find the half perimeter. Find the product. You
The
finished?
perimeter is 9,
9. Okay.
and then that means it's basically
Step by step.
That's,
No jump.
I think the area, according to my calculations, is 216.
Okay. I want to go slow. So S substitute by 9. S minus A.
That would be 4.
S minus B.
3.
C.
And then 2.
Okay. Then we take a square root. Nine give us 3. 4 give us 2. 3 and 2 we cannot go any further. Root of 6. So this gives us the area. So this formula tells us we can find the area very quickly as long as you give me the length of the 3 sides. A, B, C, then we find the half perimeter, we find the area. Okay, now I will ask you why this? How do we prove it? We checked it works, but now we want to see why. The proof of this is not easy. You can see you have a lot of factors over there. This will be something you learn in algebra about factorization. But the main step here is the area formula we had over there and the Pythagorean theorem. Okay, so I will sketch the steps. So sketch. So we start with area. Half A B sine angle C. Okay. We have used this formula many times. Okay, we square both sides because in the end, we will take a square root. So let's take a square at the beginning. Square, 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 sine square. And our Pythagorean theorem tells us, oops, so first step, area formula. Second step, Pythagorean formula. Sine square, 1 minus cosine square. The next step is the formula law of cosine. law of cosine, then square. A square. Okay, now the rest is the hard part. We have to factorize this. I said it's hard, but it's not that hard because there are a lot of, so the difference of squares, the cancellations, a square, b square, ab square on the denominator, they cancel each other. There are a lot of cancellations after simplification. So I skip a few steps to factorization. We will get s. Okay, so if you are curious, you can try to complete to fill in the gaps over there. You have a difficulty, you can let me know. I will tell you how to move forward. Okay, so this is the sketch of the proof. Any questions so far? Isabel, are you still here, Isabel? Fred. Okay, turn on the camera, Fred. Okay, yes. Okay, so this is about the triangles and the trigonometric functions. Next, we go to circles. Chapter 5. Okay, so a circle, we have a center and a radius. The center, radius. Okay. And I give 2 points on the circle. Connect them, we get a chord. And in the future, we will use notation for the arc to distinguish the chord from the arc. I will put an arrow on top of it. A, B, arc.
Excuse me.
Yes.
Error?
Well, yes, which part?
About AB. What was that?
You mean here?
No, the one below that. I mean, like, what's that ring over there for?
Okay, so I want to distinguish this segment from this arc.
Oh.
So the first one, I call it a chord, just AB. Second one, so for this one, to distinguish the two notations, I put a arc on top of it. So the
Oh,
arc.
I see. I see.
Uh-huh. Now let's see. If I pick a point over there, the distance is bigger than the radius. So now we see OQ bigger than R, equivalent to Q outside. Like outside of circle. Then given a chord, we can define two angles. The easy one, we connect the 2 points to the center. Angle AOB, the central angle. Okay. Find another point on the circle. Connect the points. We get another angle. Okay, got it. Inscribed angle. A very important property that we will use repeatedly is the connection between the two. This is called the inscribed angles. Let me check the name of this. Theorem. The inscribed angle is half of the central angle. Why this is important? Because the inscribed angle, this angle changes when the point moves on the circle. P can go over there, we connect, we get another inscribed circle. P can go over here, we connect, get another inscribed angle. The theorem tells us as long as P moves along the circle, the inscribed angle, they all equal to half of the central angle. In particular, they are all the same. very important theorem. In particular, I'll keep writing this. As long as it does not pass A or B, moves on this part. The inscribed angle theorem. Okay. The last time we gave a proof of this theorem. The proof connect as we have seen in the homework, this angle APO is the same as APAO. So in particular, by the exterior angle theorem, this is twice of this part, and this is twice of this. In particular, is twice of that by the exterior angle theorem.
Excuse me?
Yes.
What about the what's it called? Inscribed angle theorem. Oh. No, intersecting chords theorem.
No, okay, we will be there.
Okay,
It's
but I feel like
slightly different.
does it have a relation with this?
I think we will use this property to prove the intersecting chord theorem.
Okay.
Okay, so let's have 5 minutes break, and we will start again at 8:90. 5 minutes break. Okay.
20.
Okay.
Okay, thank you.
Okay, so this inscribed angle theorem is our first theorem about circles, and we will use it repeatedly. The next theorem is the intersecting chords theorem. Okay, let's draw a picture. we draw two chords on the circle intersect. One, two arbitrary chords. Your drawing can be different from mine. It all works. Okay, I'm going to label the points A, B, C, D. Okay. The intersect, I label this point E. Okay, so two intersecting chords. First one AB, second one CD. They intersect at point E. Now we have AE and BE, CE and DE. The theorem states that the product of two intersecting AE, BE, CE, DE. Okay. The product is, they are the same. Okay, so how do we prove this? We connect the 2 points AC. Straight line. Connect BD. Now we have two triangles. Triangle AEC. Triangle DBEB. EB. I wanted to show that these two triangles are similar. For this, we could apply the AA similarity theorem. To apply the AA similarity theorem, we need to check there are two pairs of angles. So this pair, they have the same measure because they are vertical angles. Angle 1, angle 2. Similarly, I claim this angle, angle 3 and angle 4, they also have the same measure. This one, because they're vertical angle. Same vertex, vertical angle. What about this one? Why? Why these two angles have the same measure? Jessica, 3 and 4. What's your guess?
I think they're, I don't know.
Because angle 3, this is the inscribed angle for A and D. This is another inscribed angle for A and D. They both equal to half of the central angle. So these two angles are the same. But because they both equal to half of the central angle. Let me mark the point O. AOD. Okay, so this is the inscribed angle theorem. The inscribed angle is a half of the central angle. This inscribed angle is half of the central angle. They both are half of the same angle. So they have the same measure. Okay. Now we have two pairs of angles the same measure. The two triangles are similar by the asymmetry theorem. Then the corresponding sides have the same ratio. AE over CE equals DE over B. Okay. Similar triangles, the corresponding AE, DE, CE, BE, they have the same ratio. With a cross multiplication, get our formula. No matter what chord we are drawing, your drawing may be different from mine, as long as they intersect at the point in the circle, then the product of these two segments, they are the same. Exactly. In our homework, I asked you to give another proof using this triangle and this triangle. Okay. The proof should be similar. It can be proved in the same way. Okay. The next theorem. Okay. Next, let's consider another circle. So we finished here. Move to the next part. Now let's imagine we start from a point at the outside of the circle. If we draw a line, it may miss the circle. It may intersect at one point, or it may intersect at 2 points. So this one is special, so we call it a tangent. Okay, I will rewrite this later. And this one is the secant line, a cut line. Okay, so let me start from a point in the exterior. Draw a line. Draw another line. Okay, now we can see the difference. This one has only one tangent point. This one has 2 points. Okay. For this one, if we move it over there, it completely miss the circle. If we move it over there, 2 intersection points. So this one kind of not it's not very stable. It may change dramatically. And this one is stable. A small change still have 2 points. So this one we call it a tangent line. Sometimes just say a tangent. If there is no ambiguity, you can say a tangent. And this we call a secant line. Sometimes just say a secant.
What's
Yes, Aaron, camera, Aaron.
what's secant?
Secant, so this is the English word for cut. It's like we cut the disk over there, cut line.
Oh,
Okay. A very important property. It's not that easy to prove, but it's kind of obvious. If we start from the center, we mark this tangent point, we connect them. You may see on the graph, we claim this is perpendicular. A very important theorem, a property maybe, property. Let A be the tangent point. Then OA. From the center to tangent point, this segment is perpendicular to P. Okay, let's think about how to prove this. What happens if the angle, if it's not perpendicular? Okay, so to prove this, let's consider what happens if two lines are not perpendicular. Okay. If it's not perpendicular, let's draw a picture. A line and non-perpendicular. Okay, so if it's not perpendicular, let's draw a perpendicular line. Not draw a perpendicular line. This will give us a right triangle. If I label this O, A, B. O, A, B. In particular, OB. will be less than OA. Because OA is the hypotenuse side. OB is less than OA. Okay. Now we can go back to the previous picture. If this is not perpendicular, we could draw a perpendicular line. With OB less than OA. However, B is outside of the circle. OB must be bigger than the radius. This is a contradiction. Okay, I'm going to write that down. Okay, so this is the thought, now the proof. Proof by contradiction. If okay, so this is a proof by contradiction. We wanted to prove that OA is perpendicular to AP or PA. We suppose, on the contrary, suppose if it's not perpendicular. If it's not a perpendicular, we can draw a perpendicular line from the center to another point on the line. Draw a perpendicular line. Okay, so because we are working on the assumption OA is not perpendicular, we can draw OB perpendicular to OA. B less than OA. Okay, so this is the picture we had over there. It's not perpendicular. We draw a perpendicular line, then OB must be less than this. The contradiction here is that, but B is outside. Circle. This implies OB is bigger than R. Okay, so now we see if we follow this figure, it's not perpendicular, then OB is less than the radius. However, if we follow this picture, we draw a perpendicular line. This point B is outside of the circle. This must be bigger than R. So now we have two cases, two facts. One less than R, one bigger than R. Which one is true? We follow this picture must be less than R. This picture goes outside must be bigger than R. So this is a contradiction. So therefore, the hypothesis is wrong and OA must be perpendicular to PA. This completes the proof. Okay, at this moment, let's recall the four proofs, four types of proofs we learned before. One is proof by contradiction. What are the remaining three proofs? Okay, Amy, give me one. Beside proof by contradiction, anything else?
Proof by contra. Wait, I think it's like position.
Contraposition. Okay, okay, that works. A contraposition. And Jessica, another one.
I don't think I know.
Okay, what about Kira? Proof by contradiction.
There's a direct proof, and then there's like
Okay,
mathematical. What's it called?
induction.
Induction?
Yeah. Okay. Okay. So a direct proof and mathematical induction. Okay. So remember this? What type of proofs? Okay, some also use proof by contrapositive. Both works. Contrapositive. Proof by contradiction. And the last one, proof by mathematical induction. Okay, so proof by contraposition, proof by contradiction. What are the differences between the two? They sound very similar. So why do I see this is the proof by contradiction, not the proof by contraposition? Okay, so prove by contraposition. It's very important to understand this. We first need to state the contraposition. What is the contraposition? This should be specified at the beginning of the proof. Proof by contradiction. We don't know what the contradiction is, but in the end, we say, oh, this is a contradiction. We don't know what it is at the beginning, but in the end, we get something contradictory. So this is specified at the beginning. This is figured out at the end. There are many different differences. Okay, just a few. Okay, so tangent line. Next, we will study a few more properties about the tangent line. I will recreate the picture. And I will draw a tangent line. Again, it don't have to be the same. As long as tangent should be fine. And I can move this. Okay. I draw another point. P tangent point A, another point B. Okay, we have a few objects. Start with a circle. And a point P outside of the circle. And the A is the tangent point. B is another point on the circle. Okay, so now we have another angle here. Angle BAP. Find the center. We connect this. Okay. This is called the P. Okay, let's check the picture. The tangent line theorem. Tangent chord, not the tangent line, the chord. Let me correct. Tangent chord. The tangent chord theorem. We have a tangent line and a chord. So we call this Tangent-Chord theorem. They say that this angle, the tangent angle, BAP, the tangent. Okay. So it's the angle between tangent and chord. So we call it tangent-chord angle. Theorem tells us this angle BAP is similar to what we had for the inscribed angle. It's also half of the central angle. Okay, let's see why is this? Why this angle is half of the central angle? We do know something. Center tangent point, we know they are perpendicular. Oh, not good. Let me try a different color. In particular, the summation of this tangent-chord angle with angle OAB is 90 degrees. OA perpendicular to AP. It implies BAP angle OAB is 90 degrees. Okay. That's the first part. How is this connected to this? But this, let's consider the triangle OAB. What's the summation of the three angles? Amy,
I'm not really sure.
the interior angle theorem. Summation of the three angles of a triangle.
Oh, 180.
Okay. That's easy. Okay, so we can see this. 180 equals the summation of the three angles. Angle AOB, angle OAB, angle OBA. Okay, so this is the interior angle theorem. Easy. And then let's check. OAB, OBA. What can we say about these two angles? Are they the same? I wanted to claim angle OAB with angle OBA. But why? Why these two angles must be the same? Jessica, triangle. Why the two angles might be the same?
Because
So two angles are the same if this is an isosceles triangle. Is this an isosceles triangle?
Yeah.
Why?
Because the
Because both OA and OB, they are the radius. They have they all equal to the radius, right?
oh yeah, they have the same radius, so it's isosceles.
Okay. It's because OA equals OB. Okay, so then this will be
What?
by the previous observation AOB. The last two angles are the same, with the summation will be twice of this one. Twice OAB. Okay, now let's compare this one with this one. We divide both sides by 2. This implies we divide both by 2, we get 90 degrees. And compare with this one. BAP, OAB, 90. This OAB, 90. They both add up to 90, so these two angles must be the same. Okay, so we check this one. Okay, different color. This one with this one. A common term. 90 degrees, 90 degrees. Therefore, angle BAP is half AOB. Okay, so this is called the Tangent-Chord theorem. It's about the tangent-chord angle. This angle, whenever we have a chord tangent, there must be half of the central angle. Okay, so we'll stop here and check. Any question about this course? I have a lot of proofs. So this is the